welcome for those who are here and those who are still coming in and joining us. Today's webinar is featuring Professor Lili Du from University of Florida. Lili is an associate professor in the Civil and Coastal Engineering Department at the University of Florida. Before that, she worked as an assistant and then as an associate professor at the Illinois Institute of Technology, IIT, from 2012 to 2017, and as a postdoctoral research associate for NextTrans at Purdue University from 2008 to 2012. Dr. Du received her PhD in Decision Sciences and Engineering Systems with a minor in Operations Research and Statistics from Rensselaer Polytechnic Institute in 2008. If you're interested in her full bio, it's available on our website or her personal website as well. So thank you, Dr. Du, for joining us. Just as a housekeeping item, this webinar is being recorded and will be shared on our YouTube channel shortly afterwards. And this webinar is brought to you by C2 Smart University Transportation Center, funded by the US DOT. So with that, I'll hand it over to you, Lili. Go ahead.
Yeah. Good afternoon, and good afternoon, everyone. Maybe somebody in the morning, just like Jucha. So thank you very much for sharing introduction, and thank you very much for Jucha's invitation for this talk. This is a very recent study about optimal dispatching of electrical vehicles for providing charging on the demand service, leveraging charging on the move technology. The title sounds a little bit complicated. I will explain all those key points in the following presentation. Again, this is Lili Du, associate professor from University of Florida. And with that, let's continue. And when I continue my presentation, I will temporarily shut off my camera because I don't want my camera and the video distract me. So at the beginning, I just want to give your overview about the state of the art regarding electrical vehicle. And we all know that it has gasoline or diesel powered electrical vehicle. Gasoline or diesel powered vehicles actually cause a lot of issues. They emit greenhouse gases and heavily depends on expensive fossil oil. Electrical vehicle, on the other hand, is a promising alternative that can address this problem and contribute a sustainable transportation system. Recent years, government and companies have tried very hard to promote the usage of EVs. However, the state of the art shows that the situation is still not very optimistic, and EV usage is still in low penetration globally, less than 8% by the data shown in 2022. There are many issues and obstacles prevent mass adoption of EVs, and this result we got from literature actually indicated several key points, such as the cost and the short driving range per charge, and the long charging delay, and the insufficient charging facilities. For all, by recognizing all these obstacles, there are pretty much, there are many existing studies and solutions trying to address those obstacles. And one possible solution could be improve battery capacity. However, this is going to make EV more expensive. And another solution could be build electrified roads. And some countries such as Korea and Korea or Sweden, they already installed this technology. But the practice show that this is a very expensive technology. Approximately, it will take 1.1 to 2.8 million per kilometers based on the literature they show. And another solution we can think about is provide battery swapping service. This type of technology has been implemented in many other countries, such as China. But in US, the current data and the information shows that it's not very popular because this technology will raise the battery ownership and the incompatibility issues. And recently, we all know that our government tried to promote high-speed charging station installation. And this actually, this is definitely is a high investment, and without good coverage of this kind of high-speed charging stations, electrical vehicles will still need to detour, and so that they can find a charge station to charge their vehicles in route. And with this kind of situation, we need to very carefully design where we should install this charging station and charging stations, and how we're going to make this charging station with good coverage and equity, and also against some extreme situations. So in this study, and we want to mention the other very new technology that's called mobile charging as a service, or mobile charging technology. Basically, this technology will enable one electrical vehicle to charge the other electrical vehicle by some emerging or new charging technologies. And I will talk about this one a little bit more. So for this mobile EV to EV charging, and we can do stationary charging. Basically, you have one truck move to the other vehicle, or basically one electric vehicle move to the other vehicle and stay there, and then use the cable to connect them and do the battery exchange. And but the study, we consider more advanced implementation of this kind of EV to EV charging technology. This could be cable charging or wireless charging. And when we integrate this battery to battery charging with the connected autonomous vehicle technology, we can enable mobile EV to EV charging on the move. Basically, when two vehicles are driving on the road, and they can have their autonomous cable connect them, and then start the battery sharing or exchange. And this kind of new technology will bring many benefits. First, it is low cost because we don't need to install many charging stations. And actually, it is an extension of existing charging station service. And this type of mobile charging service on the move will see vehicles detour and basically completely avoid charging detour or delay. So this brings a lot of convenience and flexibility for EVs cheap. And on the other hand, we already noticed that we are not able to install charging station everywhere, especially in some rural place. So then this kind of mobile charging solution will help in these areas. So by recognizing this new technology, our study think more about it. And when we do this kind of EV to EV charging, and we can have two types of the electricity providers. The first to think about it is we can have private EVs to serve as a electricity provider, and basically, when two EV driving on the road, and one private EV can, detour and help the other EV if they have the battery shortage. This is something a little bit similar to current Uber service. And we can also have another type of EV provider. That is, we call it, we use mobile charger stations to help those EV with the battery charge in route. And we think that for this private EV provider, private provider, electrical vehicle provider, it is only suitable for a high EV penetration market because each individual EV demand, electricity demand, need to find another provider locally, so that this private vehicle can help this EV efficiently without have too much detour. Or if we purely depend on private vehicle, it's very possible we're going to have the situation that supply and demand not well matched in terms of spatial service space. So, and with this mobile charging station, we have more we have more way to handle this kind of supply demand imbalance, and plus we can, you know, serve some electricity demand. I mean, basically EV, they have the battery shortage more efficiently. You know, when EV penetration is not very high. So, you know, with this kind of consideration, and we want to talk about charging as a service strategy. Basically, we want to use this EV to EV charging technology to advance the charging as a service platform. So the idea is that, you know, when in the following presentation, I will just use ED to represent the demand require battery, and EP to represent the EV that provide the battery sharing. So when ED driving on the road and they, you know, have the battery shortage, they're going to send a request to the platform, basically a centralized service platform. And this CaaS will dispatch this EP's fleet to distribute the energy. And each EP can serve multiple EDs in the trip until it's used all its energy and go back to depots. So this sounds very you know, promising service, but you know, from operation side, there are several challenges. First one, we need to carefully schedule the trips of EPs so that we can save their detour. Because when EP move to one ED, and it's possible some of their trip is idle, they don't need to serve anybody, just use extra energy. And another consideration is we don't want to have too many EPs dispatched in the, you know, road network or traffic network, because it's definitely these EPs are extra traffic. We don't want to make it, you know, cause extra traffic congestion. And another concern is because this ED ask service in route, and we think that EDs won't want to wait on the road for a long time. Usually, they want to get the service as soon as possible. So this actually is a large scale online application or online service. And this gives us the huge challenge or high requirement about the computation performance. So after recognize all this operation challenge, in our study, we want to develop a VRP problem and the solutions to satisfy this service. To develop this VRP for this CaaS service, involving this kind of EV to EV charging, and you know, clearly we want to optimally dispatch this EP to approach EDs, and then provide timely service. And but for this particular VRP, we think there are some very unique features and challenges. First is just, you know, first of all, you know, this VRP need to synchronize the journeys of EDs and EP. Basically, the demand is not a stationary point, and the ED is always driving on the road, and they have their own trip plan. And the second is the delivery. Basically, electricity delivery is not at a static spot. It's actually the delivery will be you know, will be a distance that both EP and EV and ED driving together. So these 2 points make this VRP is very different to traditional VRP. Another thing I want to mention is about the subtool issues. This usually is a technical challenge in VRP modeling and the solution process. In this CaaS service, we allow one ED to get service from multiple EPs. At the same time, each EPs can serve multiple EDs. So this type of many-to-many service will cause many subtool in the modeling side and also solution side, and we need to take care of this very carefully. And the last, as I mentioned, that this is you know, we need to serve large scale online demands, and this require us to have very good computation performance for our model. After that, you know, I want to talk about how we are going to address those difficulties in the modeling part first. And by analyzing this VRP problem more carefully, and we noticed that when we try to pair a EP and ED's journeys, and there are some important features we want to pay attention. Basically, EP is going to switch service from one ED to another one in its trip. And then this kind of switch actually have two types of modes. The number one is the local switch. Basically, the one ED pair, EP and ED pair, basically this pair is going to meet another ED at a encounter port. Basically, the point that both ED will go through, and then do a local switch without idle trip. And then the other type of switch is this EP have leave one ED and then move to another ED by an idle trip. So we call this is the distant switch. And when we do the modeling, we notice that, and this is a large scale problem. We want to make the problem can be simplified, going to benefit the computation side. So our first thought is we are going to build this VRP on a simplified network. When we say simplified, it mainly involved, those points. Basically, number one, for this network, we only consider the nodes involving encounter nodes and the origins and the destinations of EDs. So these encounter nodes are the intersections that both ED and EP pass through. And also involved, this encounter nodes is also involved that roads that ED and EP go over together. Those encounter nodes also involve the roads that two ED will go through at some time together. So, and this is encounter nodes, and build on this encounter nodes origin destination, we will simplify the trip of EDs by the chains of encounter nodes, and this will help us reduce the network size. Basically, some nodes, if even it is on the trip of the ED, but it is not going to encounter any other ED, and also it is not the origin and destination, we're going to, in our network, we're going to ignore it just based on a link. Just use the link connected to encounter nodes. So inside in this internal nodes without encounter with any other EDs will be ignored. And then those EPs providers will meet the demand and switch service at this encounter nodes or origin nodes, and then use this way we can synchronize their trips. I saw there is a question in the chat box. Shall I answer it now, or shall I just go ahead, continue my presentation at the end?
It's up to you, whatever you prefer.
So I think the question is about, is this VRP for CaaS similar to Chinese postman problem? I think, my previous explanation already answered this question. This VRP is different to those traditional Chinese postman problem because of this, the demand is on mobile nodes and the delivery is also on the move. So this makes this VRP are very different. And plus, this is a many-to-many, basically many supplier and many demand. They can have, one demand can serve more demand. One demand can get more supplier. So this is the key points to differentiate this VRP with traditional VRP, including the problem that the question mentioned about Chinese postman problem. Okay. By understanding all those unique features, and this is our mathematical model, basically this VRP model, I want to just go over the key points. The objective function, we try to minimize the fleet size, and this objective will subject to the constraint regarding to flow conservation, energy, or the demand energy constraint and the supply energy constraint, and also feasible switch constraint. For this one, I will talk a little bit more about the subtool elimination. So we can say that, when one EP and ED will meet at a node and then provide a service. Once this service is done, the vehicle will continue its trip, and EP will, either do a distant switch or, or local switch. For this animation, it is a distant switch, and go to another node, meet with the other demand, and continue the service. After this service done, and the EP is going to switch to more demands, and then, keep on going. And then in the problem from spatial side, it is possible this EP will go back to the original, to the first node N1 again. So this is the subtour actually happened in many VRP problem. And in the existing literature, there are already some well-defined constraint. You can eliminate this kind of subtour. For our problem, this is a little bit different. This is because, once this subtour happened, if we want to have this EP continuous service serve the first demand, basically ED1, then this is illegal subtour. We definitely need to remove it. However, in our problem, there's another situation is once EP go back to N1, it can continue serve another ED. Then this subtour is legal for us. So basically, if we use the traditional subtour elimination constraint, we're going to remove all this subtour, including this legal subtour. So we don't want to do that. So that is, we developed a new constraint and new strategy to eliminate this subtour. Basically, mainly eliminate illegal subtour and keep this legal subtour, and so that we can make sure our solution keeps service efficiency enough. So this subtour elimination constraint, my idea is we add extra constraint that each EPS, no matter it's to locally switch or do distant switch, it has to arrive that node before the demand leave that node. So in this way, we can, eliminate this illegal subtour, and at the same time, I want to explain a little bit. So for a vehicle leave, the time step that a demand leave a node is going to count the arriving time plus its waiting time. That means, in the whole model, we consider that one demand may reach a node, an encounter node, stay there, and wait a little bit time with the tolerance that the demand provided, and until the provider comes and start the service. I got a question from the chat box is how many EPs and EDs can travel at the same time in the same platoon? Is if there are two EPs serving one ED at the same time, will the charging speed be doubled? Or if one EP serves two EDs, is the charging service rate split evenly? That's a very good question. Actually, in my current study, or initial study, we consider each EP can only serve one ED. And it is possible that one EP have more ports and they can connect to more ED at the same time, just like one EP driving in the front, and there are short platoon ED following EP with multiple cables connected to each one. That's I checked with my collaborator at ECE, and this is actually a durable solution, but need more research to make it feasible and practically safe in reality. So for that one, I think it's definitely a very promising direction to explore in the future. And so after that, the service, regarding one EP or two EP serve one ED, or one ED, one EP serve more EDs, what's the service rate will be doubled, or those questions, I think I'm not expert in this area. Let's really need to think about how we design the battery and how the battery-to-battery charging technology is designed, I cannot give you a confirmed answer. So continue our talk about this model. So, overall, this VRP problem is NP hard, and based on, the model we have, we analyze the complexity, we notice that this distant switching actually give us more complicated variable and the constraint. It is the key complexity of the entire model. So, and by understanding this complexity, we developed clustering aided clock and write saving algorithm. And in the following slides, I'm going to talk more about this algorithm design. So to develop this algorithm, the first step, we want to talk about a machine learning aided decomposition. To develop this decomposition approach, let's first go back and look at the problem features again. And first, we notice that for those demands, they can be treated separately if their trip are not correlated at all. And also, for the service side, and we don't want to have many distant switch because it's a lot of distant switch because it's going to cause idle travels. So after we understand this point, and the next is we want to have some machine learning approach, we can understand the local switch potential, and then we can decompose all those demands. So then the first step is how we're going to quantify the local switch potential among all those demands. To do that, I give two formulation here. The number one is actually give a set of ED. Okay, let me see it in this way. So the first equation actually said is with a given ED, for example, the demand I, we try to find a set of demands that are qualified for a local switch at a given node with this given ED, okay, this given demand. So based on this set, we can have the second formulation. It counts the number of opportunities that a EP can locally switch from one ED, such as EDI, to another ED, such as EDJ. So this give us a local switch potential between each pair of ED. And here we have an example. I just want to understand this concept easily. So we have two ED1 and ED2, and we have EP. Suppose they have some, their trip have some overlap and give us some encounter nodes. And then, at the beginning, the first example, we can say they have, 5 encounter nodes over their trips. So then the local switch potential equal to 5. However, if the trip changed and they have 6 encounter nodes between their trips, then the local switch potential equal to 6. Similarly, and as more encounter nodes exist between the trip of 2 ED, and their local switch potential increase. After we can quantify this local switch potential for each pair of EDs in the pool, then we are going to build a network that each individual nodes is the ED and their connection is the local switch potential. Then based on this network, and we can do clustering and separate ED into different groups. And so that, within each group, those ED have high potential to do the local switch. Basically, those ED have high potential to share the same EPs and do the local switch. And however, between these different groups, the ED between different groups will have a low potential to enable this kind of local switch. And after we use this local switch potential to clustering different demand, and accordingly we can have the original VRP decomposed to some sub VRPs, and all those sub VRP can be solved individually. And I won't talk about this algorithm more in next slides. And so, as I said, the first step is we decompose this VRP by clustering EDs according to the local switching potential index. After that, just like this picture shows, we decompose all the demand into 2 groups. And then after that, we're going to solve this sub-VRP, generate the seed tours. These seed tours only consider the local switches. And that's going to make the original VRP much, much more easier to be solved. And don't forget, all those sub-problems actually can be solved parallelly, locally, so we don't need to, so that we can bring down the computation load very much. And next is, after we solve this solve the sub-VRP in each individual group and find those seed tours. And we don't want to stay with this solution. We want to merge these seed tours to further save using save EPs. Basically, we don't want to use many EPs. And those seed tours can be merged. Actually, every merge reduce 1 need of the EP. So, and then, this will ensure, when we do this kind of merge, we need to ensure timely service because every ED have their waiting time threshold. And we need to ensure energy feasibility of EP. Don't remember that when we merge 2 sub-tour, basically, this 2 EP will become, merged to 1 EP serve all the demand. Then we need to make sure this EP have enough energy to serve all the ED on the chips. And we have some mathematical proof to indicate the feasibility of this kind of merge, or we 100% sure that this kind of merge will generate a solution satisfy all the constraints in the original VRP. And then we, I want to mention that because of the benefit of this algorithm, basically we can solve it very efficiently so that we can, adapt this CaaS platform to large-scale online application. More importantly, it enables us to run more comprehensive experiments so that we can understand the performance of this CaaS, leveraging the vehicle-to-vehicle charging technology, and also provide some, understanding about how it's going to benefit the users, how it's going to affect the system, transportation system, and what kind of strategies we can use to improve the operations. So then we came to our numerical experiments. To do the experiments, we used the Chicago network and the Florida network as the test bed. And for the Chicago network, we assume the demand is greater than 10,000 per 30 seconds. And also we set the standard standard parameters for the battery capacity and the charging rate. And also I want to mention that experiments using 2 scenarios. One scenario is, yes, all the demand only use charging station. The other scenario is demand will co-use charging station and the mobile charging service. And we test our the performance and light, moderate, and heavy traffic congestion. And also we consider the charging station coverage can varying over in the future change from low coverage, medium coverage, and high coverage. And basically those percent is the percent of existing of gasoline charging station coverage. And then let's take a look at the computation performance first. And you can see from the table that, if we use Groovy to solve this VRP problem within 1 hour and 2 hours, and we can easily say that when the demand greater than 100, the Groovy just cannot solve it anymore. And also when the demand less than 100, our solution, this is our solution and group solution and the Groovy solution are very close. And when the demand greater than 100, and our model can still solve this problem efficiently, in particular when the demand is 10,000, and we can solve this problem within about 10 to 11 minutes. And Also, I want to you take a look at the last column about the service rate. Basically, how many demands each individual provider can service. Then we can say as more and more users using this service, then the service rate actually keep on increasing. This indicates economic scale. Basically, more users and high service rate, lower operation cost. And we also want to point out that we want to use as less as possible. This is the number of EPs we need, basically this column. So we want to use as less as possible of EPs because, as I mentioned at the beginning, the provider's EV is also sorry, is also traffic. It's actually give traffic overhead. We want to have this impact as less as possible, as small as possible. So. And next, we want to talk about the user benefit. Let's stop a little bit because I saw another question come from the chat box. So the question is for co-using case, is one ED allowed to use both CS and EPs for the same trips? For example, ED get partially charged at charge station first, then it travels together with an EP and continuously get charged for the rest of trips. For that case, thanks for the question, it's very great. And for this co-use, if I think if I remember it correctly, and if each ED, they can determine based on their location and the travel time, they can choose to use either CS basic charging station or the mobile charging. But I don't think this we allow the demand to use charging station partially charged and then on the road to find the EP to continue charge. We didn't do that. We think if they go to charging station, they will charge enough battery for them to go to their destination. Okay. So then this is the result for to demonstrate the benefit for user. As I mentioned, we evaluated the performance and the mild traffic congestion and the system. I mean, when we say co-use, that means the system coexist has the mobile charging and also existing roadside level 3 charging stations. And we noticed that if the system provides 2 type of service, and then based on what I said, that you either use charging station, finish charging enough, your battery go to your destination, or you can use the mobile charging, have multiple EP help you to get enough battery and go to your destination. Then our result shows that co-use this 2 type of service can save your travel about 50%. Basically, the average vehicle miles traveled for their trips will drop from 19 miles to 12.5 miles. And at the same time, the travel time will drop from, you drop about 40%, average value dropped from 26 minutes to 16 minutes. And in any way, this solution actually can convince us that this mobile service definitely is a great solution or extension to the existing charging station service. Is going to help save our trip and also travel time. And then next, I want to talk about the system impact. So basically, the congestion effect. And for this study, and the experiments are a little bit complicated, involve several scenarios. Let me explain it. So for the figures on the right, you can see we have 3 figures and respectively demonstrate the results from light traffic, moderate traffic, and high traffic, basically very congested traffic. And then in each figure, we have 3 curves. And I want to say the green and the blue curves represent the low and the moderate or medium charging station coverage. And the orange represent the fully charging station coverage. So then, let's first take a look at the result. Basically, I want to pay attention to the green and the blue lines in each figures. Then you can see in light traffic and mild congested traffic, for this x-axis is the proportion of traffic using this mobile service. We can see when at the light traffic condition that we can save the travel time up to 20% if 60% of the users use this this mobile charging service. Of course, after that, the benefits become less, but it still saves travel time to a certain extent. And in the mild traffic congestion, we can observe the similar trend, but we want to say that oh, sorry. For the light traffic, it's completely save travel time, but for the mild traffic, the percent is up to 20%. After that, we start to have the negative traffic impact. But in the congestion flow, only very few people use this. If only a few people use this kind of service, for example, less than 10%, and then the impact is very minor. It's just an increased traffic percent about 5%, traffic congestion about 5%. But if you allow the traffic impact, below 15%, then we can allow around 20% of users use this mobile service. So basically, I want to summarize as if traffic is light or moderate congested, and we can have a major part of users switch to use this mobile charging without affect the traffic too much. But if traffic is very congested, and we would suggest this service only used for a few users for some emergency situation. And now we want to say we want to say, of course, for just now, we only talk about the charging station coverage is low. When the charging station is very high, basically, if we invest enough and install a lot of fast chargers in the transportation network, then the results will be very different. You can say no matter traffic no matter what type of traffic, and involving more this kind of mobile charger in the traffic on the road will affect the traffic, will make traffic a little bit more congested. And this kind of situation, and we think that this kind of mobile charger probably will mainly used for emergency service for first and last mile gap, or for some low income community or rural place. But on the other hand, when we see this kind of high charging station coverage, or experiments actually assume that the fast charging station coverage will reach to exactly the gasoline charging station coverage in current network. So we think this is very difficult because faster charging station is expensive. Infrastructure is going to be very hard for us to install that high coverage of high-speed charging station in that high coverage. Okay, so so next we want to talk about the insight for operations. So we think that the battery capacity is a very important parameter for manager to consider to implement this kind of provider. And we noticed that the battery capacity and also ED's trip correlation actually will affect the service rate, basically how many vehicles each EP can serve in its trip. And then this result shows that, in this period, if we increase the battery capacity of this provider, and it definitely increase the service rate. However, after some point that, the effect is not apparently. This is because after we reach this zone, I mean, phase 2, that means the battery capacity of EP is good. And we want to further improve the service rate. It mainly rely on the trip correlation between ED. And after we, if we continue increase the battery capacity, we reach to phase 3. And we noticed that the effect is almost gone. Is because, you know, after we reach to, you know, after some period, once the, you know, the battery capacity reaches certain level is sufficient high, and then, you know, we are not able to further increase the service rate because, you know, ED's trips correlation is just like that. It just provides that much potential to increase the service rate. So this result gave us some insight that we can carefully choose the best battery capacity so that we can balance the service rate and the operation cost. And the next result I want to share with you is about, you know, it's about, you know, energy demands, energy shortage, how demand energy shortage, or when they ask the service will be the best to help the system perform more efficiently. We define the energy shortage rate equal to the energy shortage of the ED of the trip demands divided by the trip distance of the ED. And then our result shows that, and if ED recommend or, you know, asks for the service and a small battery or energy shortage, it's going to help the CaaS to improve service rate very much. And this is give us some insight that we can develop some pricing strategy to encourage those kind of demand to ask for the service when their battery is in a low shortage, rather than they almost run out of their battery and they need the service immediately or in a very short time. So this is another insight for the operators. And one more insight for that is about we test this mobile charger service for the long trip, you know, based on the Florida statewide network. And we noticed that the maximum, based on the, you know, current Florida network and also the location of those depots, and we noticed that the maximum EP service rate is around 2.5. That means one EP probably will serve 2 to 3 demands on the trips. Then they have to go back to the depots. We think that this looks like not very good, but we notice if we can, you know, then this result will give us some insight that we can still set up some pricing strategy so that we can encourage this short distance trip to use this service, and you know, to improve the service efficiency. On the other hand, we notice that if we can lift the coverage of the current charging station, and it's good, or the, you know, carefully plan the location of this charging station along the Florida network, basically, and we will help improve the service rate of this mobile charging service very much. I got another question in the chat box. So was the CaaS only scenario to solved by another algorithm? Yes, it is solved by another algorithm. Basically, each ED will only choose their most close charging station to finish their service. And the second question is, how would ED choices between different charging types considering in the CaaS Plus scenario? Oh, in our examples, we only consider fast charger. So, you know, there is no different type of charger. The third question is, according to the system impact, would ME2 be a service bridging low and high charging station coverage except for yeah, that's a very that's a very promising usage of the ME2. Agreeing with you, even though in our experiments we didn't test it. So thank you very much for this question, and I will continue my presentation. So all the above study is mainly talk about how we dispatch basically the provider to the demands. And I want to take a little bit time talk about another study just to give you a basic idea about it. And you know, to pairing supply and demand, or basically provider and demand, is not just synchronize their journeys, and we also need to synchronize their movement once this EP and ED on the same road. Basically, if the provider and the demand on the same road, and they are originally in different lanes or separated by different vehicles and in a relatively long distance, and we want to have this EP or ED can approach each other as soon as possible. But this approaching process will affect the traffic also. So especially if there are some other background traffic, such as human drive vehicles. So to address this challenge, and we developed a synchronization algorithm based on using the hybrid MPC approach. Basically, we consider the initial state of the traffic and also the location of the provider and the demand, and we threw into this input information into a prediction model, and we can predict the future state of the traffic and the distance between supply and provider and the demand. And with this prediction, we can calculate the Hall derivation of this current state to our desired state. And then we put this into our optimization model, and we calculate the vehicle movement control, and then to affect the movement of the vehicles. And then, we do this iteratively until this provider can reach to the demand, closely enough to conduct this, EV to EV charging service. And this MPC model will consider, based on my description, I hope you see that, and we will consider macroscopic traffic movement and also macroscopic traffic impact. And we also need to consider the feedback, basically feedback from the controller at each step to the entire traffic, and also the individual provider and the demand. And have a short video to show the effect. So this is the our preliminary result. That you can say, if we run our algorithm without considering traffic impact, then you can see this demand actually is slowed down in the traffic, because the red vehicle, the red vehicle actually is the demand. They slow down in the traffic and wait for the supply, and then it's block the traffic behind them. So, and if we give a very high priority for the traffic impact, then we can say we actually more actively move the movement of the supply and the provider and the demand, so that we can have this two vehicle approach efficiently without slow down the background traffic. So this is another study. So with the time limit, I don't want to go into too much too many details about these studies. And if you're interested, feel free to contact me, and we can talk more about it in the future. And overall, I want to conclude my study. And so for this study, mainly the paper we published at the bottom, this slides. And we think that, the charging as a service platform can take advantage of this kind of battery-to-battery charging and also autonomy technology. And it's going to be a very promising solution to provide on-the-move service and address the charging and range accessibility issues, to affect the mass adoption of EV in the future. And in this study, we contribute a VRP model and also an efficient algorithm so that we can generate efficient dispatching schemes to enable this kind of online application in practice. And our study noticed that this CaaS platform can save users detours, can lead to minor traffic overhead in sparse or mild traffic condition, but under low or mild EV penetration rate. However, if traffic is very congested and dispatching this electricity provider on the road will cause some traffic issues, and we need to adjust how we are going to use this technology. And our study also indicated that leveraging the fleet battery capacity control and the pricing strategy, we can, and also the energy, regarding to the demand's energy shortage and the trip length, we can improve the service efficiency even more and mitigate the traffic overhead. And in the future, we have some ongoing research and the future study regarding synchronize this kind of providers, electricity providers and demands on the road. And we are also working on how we're going to carefully design the location of charging station, considering about this kind of mobile charging service. So hopefully, we have some results coming soon in the future, and sharing with you in the future. Thank you very much. And at the end, I want to acknowledge the support of this, my grants and the project that support this study, and also my co-author, Zhanghua Chu. He is my PhD student. What is more, as I want to particularly mention that there are several ECE colleagues at UF, such as Dr. Shuo Wang and Dr. Swan Bahani. They are my collaborator working on the the big area of this kind of mobile charging, and I would like to thanks for their discussion about this research over the period. And that came to the end of my presentation. Thank you very much for your attention. I'll be very happy to answer more questions.
Thank you very much, Lili. And thank you for answering questions on the fly as they came in, which I think was contextually made a lot of sense. So it was good to have that. If anyone else has any more questions, feel free to use the Q&A box at the bottom of the screen. Joe, do you have any questions for Lili?
Yeah, maybe I can actually ask a quick question before you go to the Q&A questions. Yeah, thanks for coming and giving this talk. Really appreciate it. One of my students, Jesse Fu, who's in the audience, he's currently embarking on some research on this topic. So yeah, and he might reach out to you later on.
Great, I would be very happy to discuss with him.
That'll be great. Yeah, so yeah, the presentation was outstanding, very interesting work, and a lot of additional steps that you took in the analysis, which is really wonderful. I had a question about the model formulation from the earlier parts of the presentation. So you basically you're assuming that the EDs have a certain path that they're taking, right?
Yes.
And the EPs are trying to find a point to intercept them.
Yes.
So are you treating basically each ED is actually each vehicle and node location? Is that how it's being set up?
ED is the demand because we consider the EV on the road. So basically, you already have your trip plan. You have your origin destination. You have your trip plan. So then, at some point, you notice you have the battery shortage to sustain you go to the destination. Then you can send out the request and then point out your first points you want to have your service started, and then we will use the rest of the trips to plan which EP and we'll meet you at what points to provide service, and of course guaranteeing you're going to get the service before you run out of battery.
Yeah, I see. So the point where they're to be intercepted is provided as an input. Is that?
The point that the first available point is provided by the users, but we are not going to always stay in the first point that the user provided. That point is only used at the start of the trip. So our system or the algorithm will determine either serve this user at the starting point you provided or any other point along your trip.
Okay. And so it's kind of like selecting one node out of multiple nodes along the path?
Yes, correct. Okay. Thanks for this good question. Great question.
Thank you.
So we have a couple more questions. So the first one is the fleet of EPs only dedicated to charge EDs on the move only? Is it possible to use these EPs for other purposes? And I guess it's task when they're idle.
Yeah, that's a great question. Definitely for this study, because we think about more advanced technology about connected autonomous vehicles. So we use it for on the move charging. Definitely you can have the EP to serve some other ED. You don't need to charge on the move. You can have the ED stop at some charging station or roadside shoulder, and then the EP approach and provide the service. And as I mentioned, this could be another usage of this technology is you can have this EP driving to some community, maybe stay there for a period, using it as a mobile charging station. One possible solution is going to be, for example, some rural place, they do not have many EV demand, and around this place they don't have charging station. Then you can send this kind of EP. According to their demand pattern, you can send this EP to this rural place, maybe every day between some hours, and stay there and help to charge their EV, and then you can drive back to a depot.
Thank you. And I think there's a clarification question that was left. It's up to you, Lili, if you want to take it, or I think if you need
Yeah, I can take it. So it's continue from question 2. So if CaaS only, basic charging station only, all vehicles will use fixed fast charger. However, in CaaS Plus, some will use fixed stations. Others will be served with ME2. I mean, how the algorithm choose which ED to serve with ME2 or fixed charging station in the CaaS. CaaS Plus scenario. Okay, I think the basic question is still about, because we have the charging station service, we have the mobile charging service. For each individual ED, you're going to, how we're going to decide, will this vehicle using the charging station, fix the charging station service, or use the mobile charging service? So we set up some criteria. For example, if you're at some location, you need to think about, if you're going to use the fixed charging station, how much detour you will go, and how much time you need to stay in the charge station to charging your vehicles, even we do not count the queue, and you basically waiting time. And this is your your time, basically your cost for using charging station. On the other hand, we will try, if you use the mobile charging service, then you're going to get some other, basically no detour, but you potentially will lead some waiting time. And then you're going to get the service on the move. And then we will compare, we will always choose a solution benefits user best. And then we came out to the result that how many ED use charging station, how many ED will use mobile charging station. And then we count the benefit to use mobile charging station. Do I answer your questions?
Yes, so thank you for your answers and thank you for your presentation. I think with that, we'll wrap up today. We're over time, so thank you for staying a little longer than planned as well. And for a great presentation. As a reminder, this video will be made available on C2 Smart's YouTube channel and on our website. You can reach Professor Du at her email or contact information if you need it, which is available on our website as well. Thank you, Lili, for your presentation, and thank you all for attending. As a reminder, this webinar was brought to you by USDOT UTC C2 Smart Center. Thanks, Lili.
Thank you very much. Thank you very much for the invitation and also all the great questions and the discussions. It's my great pleasure to talk about and share with you these studies.
Thank you very much.
Bye.